Welcome everyone. We're going to talk about parametrization of curves now. So we can talk about curves in 2-dimension or 3-dimension. So if you have a curve in 2-dimension, you can write it as a vector valued function r of t, which will be given as two components, x of t and y of t. So that's our parametrization of that curve C in a vector form. And of course, we're going to give interval for t. T can go from anywhere from A to B. So that's how we're going to parameterize a 2-dimensional curve. Here, you have to notice that both your x and y value will depend on this new parameter, which we're calling t. So this is for 2-dimension. Now for 3-dimension, we can also represent the curve C in vector form, r of t, in a parametric form as x of t, y of t, and z of t. So you have three components that will describe the path of this specific particle. And again, we can let t go from A to B, or you can let t be -infinity to +infinity. It wouldn't matter, depending on the path that you're describing. So these are the parametrization of some curve that we're talking about, could be in 2D or 3D. Now, the most common or most general parametrization that we would like to use is let one variable be t, and the other variable will depend on that variable that you selected to be t. Let me show you some examples to illustrate this idea. Let's look at this example. We're going to find a parametrization for this curve, which is the left half of this parabola, y equals x squared plus 2x. So now let's take a look at the graph. So we know it's a parabola that has a x-intercept at 0 and -2. So let's suppose this is the curve we're looking at, something like this. So we only want the left half, so it's gonna cut off at -1 right here. So we only want to parameterize the left side of it, so only this portion right here. Okay, so how do we do that? Well, we'll pick the natural parametrization. Since y is depending on x, we can let x to be our choice for t. So we replace x with this variable t, which is our parameter. Then y, it's going to be expressed in terms of t. So it will be t squared plus 2t. Now, if you look at the graph, we're restricting x to be less than or equal to -1, so that we only get the left side of the parabola, which means for this parametrization, we're also going to restrict our t values. T is going to go from less than or equal to -1. So when t is -1, we are right here. This is when t is -1. And when t is -2, we are right here. T is equal to -2. And as you can see, the curve is just going to go that way. So you can choose the direction. Looks like this is the direction of the curve. So that's the parametrization. Now, if you want to write this in a vector form, we can say that r of t, which will describe the path of some particle along this curve, just the left side of it, you can write this as x is t and y is t squared plus 2t. And we're letting t to run from -infinity up to -1. So that will be our vector form of this parametrization of this curve. Here's another example for us. We're going to find a parametrization of the line segment connecting these endpoints. So let's suppose our first point is right here and the second point is right here. So let's suppose this is -1 to -3, and this is the point 4, 1. So we want a path that will go from the first point to the second point, and you want to parameterize that. So you want to write it as a vector form or a vector equation of this line segment. So we know our vector form of this line segment is going to have an initial point, RO, plus the direction. So we'll have to figure out the direction times our parameter t. So let's figure out the direction of the line. So we'll figure out the vector B by simply taking the second point, subtracting the first point component-wise. So we will have our direction as 4 minus -1. So I subtract the x components of our point, and then the y components will be 1 minus -3. So this will give us our direction vector V as 4 plus 1, that's 5, and then 1 plus 3, that would be 4. So that's our direction of the vector. We'll place that in here. And our initial point is going to be this one because we're moving from this point towards that point. So we want the direction to go that way for r of t. So that means our RO, it's going to be this point, and we'll write it in vector form. So our parametrization of this line segment, R of t, would be RO, which is -1, -3, plus the vector V, which is our direction, 5, 4 times t. And now we need to put the boundary on t. Well, when t equals 0, this will disappear, so we're going to be at the initial point. So t will start from 0. And then when t equals 1, our vector equation will become -1 plus 5, that will be 4. And then -3 plus 4, that will be 1. So when t equals 1, we're going to be at the final point. So t will range from 0 to 1. So this is one way to write the equation of r of t. R is parametrized. We parameterize this line segment. Now you can also write it as following way. So you can also write this as component-wise. So x component will be -1 plus 5t, and the y component will be -3 plus 4t. Again, we're going to let t go from 0 to 1. So that will be another way you can write the parametrization of a line segment going from point A to point B. For this particular example, we're going to parameterize the intersection of this paraboloid and the intersection of the paraboloid and the plane z equals 4. So if you were to draw this is a three-dimensional surface. So we have our three-dimensional space right here. Z equals x squared plus y squared. We know that's a paraboloid. Center at right here, passing through 0, 0. And z equals 4, it's going to cut right through it. So something like that. So as it cuts through it, the intersection is going to be this right here. So that will be the intersection, which will be a circle. So we're going to parameterize this. This is the intersection. So how do we parameterize that? Well, let's figure out what's the equation of the circle is. So if z is equal to 4, we're going to get x squared plus y squared is equal to 4, which means this is a circle center at the origin with radius 2. So the natural parametrization of a circle is often, if it's centered at the origin, is going to be, you can think of it as r cosine t, and y is equal to r sine t, where r is the radius of the circle, centering at the origin. And this will give us the orientation going counterclockwise. So the orientation of the curve would be counterclockwise, and we will let t go from 0 to 2 pi. That'll give you the entire circle on the xy plane. So if you project it down, that's the image we will see. So in this case, our r is 2, so we're going to go ahead and place that here. So our parametrization of the curve of the intersection would be x equals 2 cosine t, y equals 2 sine t, and z is going to be just 4. So that means you can write the vector valued function r of t, which will parameterize the curve of the intersection, as 2 cosine t, 2 sine t, and z is 4. And of course, t, we're going to let it range from 0 to 2 pi. For this problem, we're going to do something slightly different. So we're given the parametric equations, and we are going to find the Cartesian equation for this parametric equation. So let's see how we're going to do that. So we're going to go ahead and do the following. So here I'm going to take this equation and solve for cosine t. So you'll have x over 4 is equal to cosine of t. And then here I can also solve for sine of t. So you'll have y over 2 is equal to sine of t. Now we know from our previous knowledge that sine square of t plus cosine square of t is equal to 1. So if I square these components, for example, here for this one, if I square it, I'm going to get x squared over 16. And if I square the second one, I will also get y squared over 4. So pretty much we can make the substitution. Sine square of t plus cosine square of t, we know that is equal to 1. So if we substitute them, we will have y squared over 4 plus x squared over 16 is equal to 1. So that is the Cartesian equation for this particular parametric equations. Now, what is this? This is an ellipse actually. And we know how to draw it. Its major axis is the x-axis because the radius along the x is greater than the radius along the y. So if you're to sketch this, let me show you how that would look like in case you're not familiar with ellipses. So here's our x and y axis. So this will be a picture that will look, so not quite that, but so it'll look something like this. So hopefully now I can draw it. All right, so something like this. This is what we're looking at. So along the x-axis, we're going, the center is 0, 0. So along the x-axis, you go 4 units this way, and then 4 units this way. And then along the y-axis, you're going to go 2 units here and 2 units here. That'd be -2. Now, if you were to trace the path for this particular equation, so we're given t is going from 0 to 2 pi. So when t equals 0, our path, so cosine of 0 is 1, sine of 0 is 0. So we're actually right here when t is equal to 0. And then, so we know cosine is going to be 1, and so x is 4 and y is 0. And then when t is equal to pi over 2, you're going to get x is equal to 0, but y is equal to 2. So you're going to be up here. So the direction of the curve is going this way. So this is the value when t is equal to pi over 2. And you can also check if t is equal to pi, your x value is going to be, so again, plugging in for cosine here, we're going to get -1. So our x coordinate will be -4 and y coordinate will be 0. So we're going to be right here when t is equal to pi. So as you can see, the direction will go this way. And then as you hit 2 pi, you're going to get at the same place as t equals 0. So that's the path along this parametric curve or the ellipse in Cartesian form. All right, I hope this helped you understand parametric equations and how to parameterize curves as well. Take care, guys.